when you're doing a reaction, whether it's in a lab or a reaction that's just naturally occurring in nature, oftentimes you have more of one thing than you need to react all of the other item that's reacting. That would be, so the one that you have more of would be known as your excess reactant, and then the one that is going to run out and make your reaction stop is the one that limits how far your reaction can go. So limiting reactants are important because you can't predict how much you're going to get from a reaction if you don't know which one's going to run out first. So we're going to call that predicting correct theoretical yield. And we're going to use the theoretical yield term more later, but it's just basically in an ideal world where all of your reactions go to completeness and you don't have any impurities and your lab procedure is perfect and you get everything that you're supposed to get out of it, your theoretical yield would be equal to whatever stoichiometric value that you produce. Another thing that is good about limiting reactants is if you have a reactant that is super expensive and you want to make sure you use all of it, it would be important to put more than enough of the other stuff that it's reacting with in the reaction as well, so you can react all of the one that is expensive. So it's important, especially if you're trying to produce a product, and that's going to be something that you market, and you would want to make as much money as you can off of what you're reacting to begin with. So I don't know why I'm not able to write right there. Reactant. So it's important to be able to use all of the more expensive reactant, and it's also important because you need to recognize that a reactant can run out. Okay, so I've got a couple problems set up here. I've seen about, a whole bunch of different ways on calculating limiting reactants. Some take longer than others. Some are more confusing than others. As long as you understand the way you're going to do it, and you can do the process properly every time, then you're going to be able to find the limiting reactant. So, problem 1 gives us 100 grams of sodium, 100 grams of iron 3 oxide, and it asks how many grams of iron here is produced and how much excess reactant remains. So we're going to run out of one of these two things before the other. So we need to figure out which one limits us, and then we'll be able to know which one's going to have some remaining. So first thing we need to do here is balance our chemical equation. Let's use this color for that. Let's see here. We've got, most like oxygen is the only one that's in both compounds. Iron and sodium, we can adjust them as necessary. So let's get our oxygens balanced. So if we put a 3 here, we now have 3 oxygen on this side and 3 oxygen on that side. So 3 on both the left and the right. So we've got 6 sodium over here, 3 times 2. So we need a 6 here. And we have 2 iron on the left, so we need a 2 there. And then our oxygens are balanced. So that one was pretty easy to balance. Let's identify that we needed to balance the oxygen first, and then everything else came together. So the next step in this is determining how many moles of sodium we have and how many moles of iron 3 oxide we have with our 100 gram values. So to calculate the sodium, we need to go to the periodic table. Sodium has a molar mass of 22.9, we'll just say 99. 22.99. So sodium (22.99 grams per mole) equals sodium, and that means that we have 100 grams, and we are going to divide by 22.99. So let's go to our calculator. 100.0 grams divided by 22.99 grams means that we have 4.3497 moles of sodium. We'll call it 4.35. I need more significant figures than that. Let's call it 4.3497. Let's go ahead and moles of sodium to begin with. We also have iron 3 oxide, so let's calculate the molar mass of iron 3 oxide. Iron has a molar mass of 55.845. And we have 2 of those. And then we also need to look up oxygen, which is 15.9994. And we have 3 of those. So that will give us our molar mass of Fe2O3. So 55.845 times 2 plus, we'll put it in parentheses, 15.9994 times 3 equals 159.6882. grams per mole. So we have 100 grams. We're going to do the same calculation we did for sodium. Times by 1 mole over 159.6882. And we will find that at the beginning we have 0.6262 moles of Fe2O3. So those are calculations we've been doing, consistently getting the same answers. So we know how to do those calculations. And now we need to move on to the limiting reactant. So there are several ways to calculate this. And like I said, it doesn't matter which way you choose to do it, as long as you can always get it right. On this problem, I'm going to show you a way that I would go ahead and do it, just because I already have to find how many grams of iron there are. So what I would do is I would figure out how many moles of iron each of these would produce if I had all of it used up. So to do that, I'm going to multiply by my molar ratio so I can get rid of the moles of sodium and find the moles of iron. So multiply by 2 moles of iron, which I get from my coefficient here, and divide by 6 moles of sodium. And that one and this one here, I will multiply by 2 moles of iron and divide by 1 mole of Fe2O3. So since I've got that one in the calculator already, I'm going to do it first. So we're going to get the answer to this one first. So we just need to multiply it by 2. We see that we get 1.2524 moles of iron. And what that tells us is if all 100 grams of Fe2O3 were to react, we would produce 1.2524 moles of iron. Now we're going to take our 4.3497. We're going to multiply by our molar ratio, which is 2 divided by 6, or we could have just divided by 3 there. And we get 1.4499 moles of iron. Okay, so now that we see that if all 100 grams of sodium react, we get 1.4499 moles. But if all 100 grams of iron 3 oxide react, we get 1.2524 moles. So we got to say which one of those is smaller, right? So when I run out of iron 3 oxide, I'm only going to have 1.25 moles produced. So that means I have not used all of my sodium, because I can produce more than 1.25 moles of iron from that amount of sodium. So iron 3 oxide is limiting how much my reaction can go. It's saying, hey, you're going to get to 1.2524 moles, and then you're not going to have any more iron 3 oxide to react in this situation. So we would take this number, because it's the smaller number, and we would go ahead and calculate our grams of iron, how much Fe is produced. So we're going to take 1.2524 moles. Molar mass of iron we've got here is 55.845. 845 grams over 1 mole. And we get 69.64 grams of iron. Will be produced. Okay, so that's all fine and dandy. That answers the first part of our problem, right? How much iron is produced. But it doesn't answer the second part of our problem, which is how much excess reactant remains. So we didn't use all of our sodium, so let's figure out how much sodium we have left over. So to do that, I'm going to go back to my 1.2524 moles, because that's how much I ended up producing. So from there, I can easily go back and figure out how many moles of sodium were used by just using my molar ratio in the opposite direction. So let me go to a blank page. So 1.2524 moles of iron was produced, and we need to figure out how much sodium we had left over. So we're going to multiply by our molar ratio from our balanced chemical equation, which if we go back over here, every 2 moles of iron that's produced uses 6 moles of sodium. So we're going to multiply by 6 and divide by 2. Because we want 6 moles of sodium over 2 moles of iron. And so essentially we're just multiplying by 3. We get 3.7572 moles of sodium were used. So now we take our molar mass of sodium, which we already looked up as 22.99. We're going to multiply that times our 3.7572 moles. Our moles will cancel out, and that will tell us how much sodium was actually used in grams. So let's take this 22.99 times 3.7572. And we get 86.378 grams per mole. Not grams per mole, just grams of sodium. And we started with 100 grams of sodium. So we will subtract our 86.378 . 100 minus our previous answer, and we get 13.621972. It wasn't 69, it was 62.219. And then addition subtraction problem, that's our farthest right significant figure and our least accurate number, so we would round here, and we would say that we have 13.6 grams of sodium remaining.